I represent a team of about 100 analog RF and microwave designers, and we make lots of cool stuff, amongst others ultra-wideband, which I'll tell you something about today. So first, this is my introduction. I'll talk a little bit about what's ranging and what actually is a problem. We'll discuss time of flight, impulse radio as a solution to measure time of flight, and spectrum usage, of course, as the accompanying problem. We'll look at 4 different ultra-wideband transmitter implementations to sort of bridge the gap for your understanding between the end application and what's actually needed at transistor level to make it happen. So, first of all, ranging. Ranging, if you look it up in the dictionary, it's basically knowing how far something is. And knowing how far something is, you can take ranging to the next step. If you know the distance, not only to 1 point, but to 3 or more points, then you can do trilateration, which is what you do with your compass on a piece of paper, and then you know where you are. So that's really cool. And as we discussed earlier, we have GPS, which honestly, I must say, is extremely cool because of satellites and rockets and global coverage and wow. But in all honesty, it's not accurate enough. It has an accuracy down to a few meters. And it doesn't work indoors. So there's a very clear gap. Let's solve that. Now, GPS and UWB, they have two things in common. They both have a 3-letter abbreviation, and they both work by measuring time of flight. But what's different is, well, more or less everything else. And as said, GPS is the global stuff. For a company like mine, a key point we're addressing is the car key question. Where is the car key? Around the car, is it inside or outside of the car? But it's a lot wider than that. It's about air tags and other smart tags. And you can fundamentally, well, you can philosophize about all the beautiful things you can do about entry control system, find my whatever, find my pet, gaming. If you know down to a very high accuracy where something is. So the topic of today is how do we do that? And the answer is time of flight. And time of flight is very, very simple. C is 3 × 10⁸ meters per second. So if we want, let's say, 10 centimeters of accuracy or so, which sounds ballpark reasonable, then we need to measure time with an error of about 0.3 nanoseconds. And it works somewhat like this. On the x-axis on this diagram, I've drawn the distance. On the y-axis, I draw the time. I start with an initiator. That might be me. I send out a pulse. The pulse travels with the speed of light to the responder. The responder takes some time to receive that pulse to send me a reply. And that reply comes back to me. And if I can measure the time from when I send something to when I receive an answer, and if I know, of course, what the time taken for the reply is, then I can calculate the time of flight. And if I know the time of flight, and since I know the speed of light, I can calculate the distance. And you don't actually need to stop at one pulse. One pulse will tell you how far something is, but it's interesting to take it one step further, and we can take actual data packets, and we can send data to there and back. That allows me to do cryptography, and I can make secure ranging, so I can know for sure that I'm receiving my own message back. I can get all sorts of data from the responder, for example, the T reply. And by the way, this is the case for an active responder. You're also allowed to think about passive responders. And in that case, you can do something like this, send out a pulse, get it reflected off a passive object, and you can do something which looks very much like indoor radar. So, how do we measure time of arrival? Well, we use something called impulse radio. And impulse radio means we make a very short pulse. And this pulse needs to be, well, short enough, and basically it needs to have a sharp leading edge so that the arrival time of this pulse can be detected with the required accuracy. And if you look at a pulse like this, it's about 2 nanoseconds wide, and it has a rise time of a little bit under a nanosecond. And then you envisage, hey, could I make a receiver that could receive a pulse like that? And then could I detect the time of arrival with an accuracy of you know, ballpark 0.3 nanoseconds. And the answer is we can do that. So we set up this 2 nanosecond pulse. It has a fast rise time, about 1 nanosecond. The carrier frequency, well, there has to be some sort of carrier frequency. It's a radio pulse. We want it to propagate. So we can choose a little bit. So that's looking good so far. But if the pulse is 2 nanoseconds wide, then the bandwidth I need is about 500 megahertz. And that's a lot of bandwidth. So we go to the regulatory guys and we say, give us 500 megahertz of free spectrum, please, because we want to do indoor positioning and ranging. And here's your electromagnetic spectrum, all the way from DC up to 300 gigahertz. And the answer is no. Because it's completely full, of course. And all sorts of useful applications are making use of this spectrum. And 500 megahertz of spectrum, honestly, maybe, you know, if you were living in 1920 or thereabouts, we could debate that. In actual fact, Marconi's first transatlantic communications were using this sort of ultra-wideband techniques. They were outlawed in 1934 because of interference reasons. When we wanted more than one transatlantic link, this was no longer an acceptable option. So we're stuck. But we don't take no for an answer, so we ask again, and please, please. And eventually they said, okay, guys, look, you can do this. You can have your 500 megahertz of spectrum, but you have to be really, really, really quiet so that nobody has a problem with you. And it's a little bit like what we're doing inside this room. It's okay to be talking to your neighbor, as long as you do so quietly, nobody else hears that. And then it's okay. Otherwise, my channel. I'm the green one here. So ultra-wideband, you have to be really, really quiet so that we can coexist with other users of the frequency band that are transmitting at the same time. And the difference is not small. Wi-Fi 802.11a and ultra-wideband, we're 60 dB down. And 60 dB sounds benign, but as always with the log scale, it's not, and it's 1,000,000 times. So you have to be 1,000,000 times more quiet than your Wi-Fi transmitter before you're allowed to do something like this. Now the FCC in America, that's the first regulatory body, they're actually quite quick. They said, okay, you can have your ultra-wideband spectrum, you have some room to play with at this very low power level, but for this to have any hope of worldwide success, we need to have worldwide standardizations and worldwide permissions. So as time went on, you saw different countries allowing different frequency bands. And you know, you can look through this and you can say, oh, there's a cross-section here where most countries will allow me to operate my ultra-wideband devices. And so just for your understanding, there's an IEEE standards that defines the bands and the modulation. That guarantees interoperability so that your Apple phone will work with your BMW car and your Samsung smart tag, because if there is no interoperability, this doesn't stand a chance in the marketplace. And then the local regulatory bodies in America, Europe, China, and Japan define exactly what is allowed. So what's the maximum output power you're allowed to, and where do you have to really shut up? This is an example of such a regulatory mask. And you will recall a few slides back, I said you have to be very quiet. The very quiet level is up there. This is the 500 megahertz of bandwidth that you're allowed to transmit. And the yellow line goes down way outside of the band of interest, telling you you have to be really, really, really quiet in all the other places. So basically what you need to do is you need to make a radio transmitter that makes a waveform, something like this. This stays neatly below the yellow mask over all frequency corners. And it needs to stay there over all process, voltage, and temperature corners. So you have to be, you know, pretty confident that your design is robust and good. And if you do that, then you did a pretty good job. So today, I want to talk a little bit about the radio transmitter that produces such a signal and produces such a signal very well. Now, the transmitter has a number of requirements. So first of all, we said it should generate a 2 nanosecond pulse. It should modulate its polarity and its position, so we can make positive, remember we want to transmit data across this channel as well. We can make positive pulses and we can make negative pulses, and we can make trains of pulses, and those pulses can be partially overlapping. There's a little bit extra difficulty, but nothing that can't be solved. The pulse is the slow outline here that's marked in black. The RF frequency of a few gigahertz is here drawn in red. So you have to upconvert to the correct center frequency, you have to amplify to the correct output power, you have to filter the output so you make sure you're not emitting anything out of band, because that's not allowed, and then you have to do all of that with acceptable power conversion, with acceptable power consumption. So you're all students, at least I'm told you're all students, so you scratch your back, you scratch your head, and you ask yourself, how would I do that? So you make what I call a textbook implementation. You may talk to your professor who knows radios and say, how would I make a radio transmitter like that? And you might come up with something like this. You say, okay, I have my data in, it's a few megabits per second. I need to sort of make a digital signal processor that generates nicely shaped pulses. I want to be able to modulate the polarity because I want to flip it positive or flip it negative. I push it through a D2A converter. I need a clock generator, maybe 2 gigahertz, 2 gigasamples per second or so clocking this duck. I need to low pass filter it, so I'll have a nice pulse here. Then I use a local oscillator. This is my gigahertz level oscillator. And in radio speak, the local oscillator is always the oscillator that is on your side as opposed to the remote oscillator, which is the one you're talking to. A mixer, a power amplifier, maybe a filter, a bandpass filters to suppress lots of spurious, and then you can go to the antenna. So this is what you have to make, and you have to take care, and this can be done, and has been done, and you have to take care of the right level of power consumption, because if we want all of this to be battery operated, it better be at a very low power. The area has to be under control because we want to sell millions and billions of these, so if it's not extremely cheap, it won't fly once again, and we have to make sure spectral performance is under control. So what I'll do in the next few slides is draw you through 4 different recent implementations of this and try to show you each and every time how you start with the textbook approach, which is on this slide, and see what the real implementations look like. And to do that, I'll be looking at the ISSCC, the yearly San Francisco conference, the Journal of Solid-State Circuits. If you don't know what that is, look it up, it's important, and previous editions of this conference. So the first one is from Singh and his team. It's a 4-year-old implementation from the Journal of Solid-State Circuits. And what you see here is, I would say, a very innovative and simple way of making this 2 nanosecond pulse. Because what we want is some sort of shaped 2 nanosecond pulse, and what they do is they take the pulse, then they put it through a number of analog delay cells, then they add all of this together, and the outcome then is an envelope which closely resembles the pulse shape we're looking for. He then puts all of this into a switched capacitor power amplifier, and the switched capacitor power amplifier, again, is an interesting topic to read up on if you're interested. The switched capacitor power amplifier consumes power only when there is data. And that's a very useful property because our data rate is actually quite low, and this whole transmitter is sitting actually idle for the majority of its life. So having circuits that are consuming no power at all when there is nothing to do is a good idea, and it's an interesting trend. You see it elsewhere as well. So this is the pulse generation, simple, efficient, in an analog way. This is the switch-capped power amplifier. And there's a similar innovation here on the local oscillator generation. You take, I think, a number of inverters, put them in a cross-coupled loop, you can make an oscillator like this. So this is how to make my gigahertz range clock. And they use an injection-locked ring oscillator. And the interesting thing is it doesn't use an inductor, which is nice because it means the size is actually very, very small. Also, because the Q here is low, it will start up instantaneously, and that's brilliant because it can start up at a moment's notice. You kick it, and boom, it's on, and it's on target frequency. Of course, something like that you make on chip, you will find it spreads by 20 or 30% the center frequency, so you do need to calibrate it beforehand, but that can be done before you start transmitting. And there's a nice trick here where they make an instant phase lock to a relatively slow reference clock. So he makes an oscillator, a local oscillator, this is the gigahertz range oscillator, and it can swap its phase at a moment's notice. So I promised you a comparison to the textbook implementation, and it looks somewhat like this. There's a number of blocks here that have been eliminated. So I say that's a green cross for elimination. That's good. The local oscillator, we saw it comes very small, very fast startup. So it gets a green check mark. And the pulse generator here, plus mixer, plus power amplifier, all integrated more or less. So I've provided that with a nice and compact green dotted line. So that's one way to actually do it. But there's more ways to do it. So Chen and the team, next year, ISSCC, they said, well, you know, actually, we want to be able to produce multiple overlapping pulses, and that's hard, or at least that requires calculation of the correct values, because in this part of the waveform, I have multiple pulses overlapping. This is hard, and we'd like to eliminate that a little bit. And they say, well, we'll do a lookup table in memory, and then we can generate out of a lookup table the 2 nanosecond pulse. But how do you do a lookup table? Well, they say, no, we have multiple pulses. In this picture, they are red, blue, and green. Up to 3 pulses can be overlapping, but that still keeps my lookup table more or less under control. So the nice thing now is they have full control over the pulse shape. And the pulse is no longer a simple triangular pulse, but it's nicely crafted to fit inside the spectral mask, and you don't need to calculate any data values on the fly. And that lowers digital overhead. And lowering digital overhead is important and is an important theme, because you may have learned or you may have caught on that the analog people like to think that digital is free in terms of power and in terms of area. Do a little bit of calibration and a little bit of post-processing, that's good. But in this specific application, the data rate is relatively low, but the bandwidth is very high, and making all of these beautiful pulses at very high data rates is actually expensive. So we do want to take care, limit the digital overhead. The next thing they do is they make a mixing duct, which is a combination of a D2A converter at the bottom. So the different data lines go in, they are summed in the current domain, and then on top goes the mixer. And this is actually an example of what your textbook calls current reuse. And what it basically is let's not put the circuits next to each other in a left-right fashion, but let's put them on top of each other. And all the current that is required for the mixer here is actually reused for the duct. Of course, at half the supply voltage. But it is a way in which you can optimize your circuits and eliminate a little bit of power consumption. So again, back to the textbook view. What happened here? Well, the pulse shaping DSP and the polarity generation is addressed with a lookup table, and then there's a nice tight integration of a D2A converter, a low-pass filter, and a mixer in a single mixing duct. So this is another way to get where you want to be. And another one, I think I'd like to talk, this is the next year's, 2023. I found this one in the ISSCC. And here, again, we are trying to keep the digital under control. So what they propose is, guys, let's not make a classical linear duct, but let's make a duct that is taking coarse steps at the extremes of its reach, and that is actually making fine steps in the middle. And this comes out of the system insight that the in-band performance actually is not sensitive at all to the step size, and you'll be doing fine. But out of band, where we need to really, really, really be quiet, what he does, or what they do, is they propose this non-uniform quantized DUC with 5 bits, and you get a lot better performance here than you would otherwise there. And that can make the difference between passing and failing your spectral mask tests. So we've eliminated one bit, and in general, understand your application and tailor your DUC to it. As Chris told you, making competent DUCs, some people spend a lifetime doing that. And we make accuracy only where needed. And in this case, it's the side lobes in the spectrum. So again, what happened? Well, the pulse shaping DSP, the non-uniform DUC. So now we've lowered the number of bits required here, again, to save power and to save digital overhead. The final one I'd like to talk about is from my colleague, Erik Oliman, who presented this at last year's ESSERC. And actually, this is one of the most integrated solutions. And what he does, he takes a single, I would say, highly digitized cell that is both taking a data input, a polarity input, the local oscillator input, and then into a diff pair that provides current in one polarity or in the other polarity to the power amplifier. And this is all in one. And this is a unit cell. But if there's one thing that Cadence is really good at, it's copy-paste of unit cells. So it's a single unit cell, but implemented 512 times. So he makes a very nice 6-bit implementation here. And the other nice thing about this is that the power amplifier, which is this part here, is actually off again when no data is being transmitted. So that's another theme you see in all the implementations. What he also does, he says, well, in this case, I've integrated everything, so I cannot put my anti-aliasing low-pass filter behind my DUC because I'm going straight into the RF domain. So he says we'll address that by making interpolation with different clock phases and then get some sort of acceptable impulse response, and then you can eliminate the spurious in your output spectrum and satisfy all the spectral masks. And the end result is actually very small. It feeds into the power amplifier, which is inductively coupled. And you get full flexibility here in the digital domain to optimize your pulse shape, to optimize however you want this to fly. Back to the textbook picture, what happened here is, well, everything right from here all the way to here integrated into a single cell to satisfy actually the same requirement. So, in conclusion, I've shown you 4 different implementations of an ultra-wideband impulse response or impulse radio transmitter to the textbook solution. And what I want you to take away from this is that, yeah, the textbook solution works, but what you see is that the actual industrial implementations, they take a lot of effort to reduce digital complexity. Remember, data rate is low, so digital in this application, and the applications are battery operated, so digital is not for free in terms of power. Combine functions, if you can, make it small, make it power efficient. Duty cycle everything that's off. So if parts of your transmitter is not required now, but are required in 10 microseconds from now, let's turn them off. And stay, and this is not trivial, within the permitted spectral mask. But then, we were given, I think, 500 megahertz to play with. So this, I think, we give back to the community. In conclusion, I would say we're just getting started, and you see an exciting new application like this pop up, and you see very rapid evolution of the state of the art in conferences, in journals, and in open literature. I'd say to you guys, welcome on board, and expect to see new and better ideas in the next few years.